Paid, rush, approved are some of the terms routinely stamped onto documents. Professionals such as engineers have their official stamps too. For years, you had to dab the stamp on an ink pad for each impression. Nowadays, you can get stamps with the ink built right in. The process begins with a design that either the stamp company or its customer creates with standard graphic software. They print the stamp design onto paper using a high-quality laser printer. Then place the printout under an imaging camera. They feed in a blank sheet of negative film. Then photograph the printout. 30 seconds later, out comes the negative. The design is light, the background dark. Now they can begin making the mold for the stamp. They apply the negative to a plate of light-sensitive polymer, a plastic-like material. Then they vacuum out the air to prevent defects in the mold. Then they expose the polymer plate to ultraviolet light for approximately 3 minutes. The UV penetrates through the light part of the negative, the stamp design, and hardens the polymer underneath. The rest of the polymer is shielded by the dark portions of the negative, so it doesn't change. A wash cycle then scrubs away this unhardened polymer, leaving behind a perfect mold in the shape of the stamp. Now they cover the mold with a sheet of synthetic resin called Bakelite and put it into a machine called a vulcanizer. The machine heats the Bakelite to just over 309 degrees Fahrenheit, then forces it into the mold using 2 to 3 tons of pressure. After 4 minutes, the Bakelite stamp is ready. To be more productive, the factory actually molds several stamps at a time. Next comes the built-in ink. They screw the Bakelite stamp into what's called the pre-ink mold. Then pour in a mixture of ink and gel. They cover the mold and vacuum out the air, a process that takes 12 minutes. The mold then goes into a heat press for 17 minutes. The press applies 2 tons of pressure to expel excess ink and heats the ink gel to about 260 degrees Fahrenheit, transforming it to roughly the consistency of a marshmallow. So it won't overcook, the mold goes onto a special cooling table for 12 minutes. Next, it's set out to cool for another 45 minutes, this time on newspapers, which soak up more excess ink. Finally, they wrap the mold in paper towels and newspapers and vacuum out the last drops of excess ink. Then they quickly seal the back of the stamp to lock the ink in. Now they can cut apart the individual stamps. They glue the stamps by hand onto the base of the stamp handles. Before they're shipped out to the customer, all stamps undergo a quality control check to make sure they'll leave a lasting impression. Rummage through a do-it-yourselfer's toolbox, and chances are you'll come across a putty knife or two. They come in several widths, So whether you're scraping off paint, old wallpaper, or installing drywall, there's a putty knife that's the right size and shape for the job. These putty knife blades are made of steel that's flexible and durable, due in part to its high carbon content. Production begins with workers feeding steel sheets into a press, one by one. The press's cutting die punches out a blade for the type of putty knife they're producing. The next press punches 3 rivet holes in the handle portion of the blade. These are for attaching a hard plastic handle. For models that will have a handle made of a softer rubber-like plastic, they fishbone the handle portion of the blade so that it'll grip the plastic. Steel has to be heat-treated to gain its full flexibility and strength. First, they submerge the blades in a bath of molten salt. The heat is intense, 1400 degrees Fahrenheit. The blades soak for about a minute, the time it takes for the metal temperature to rise to that of the tank. As it does, the steel's molecular structure begins to change. From here, they transfer the blades to 2 successively cooler salt baths. That quenching, as it's called, further hardens the steel. The blades are then tempered in an oven for 8 hours at 400 degrees Fahrenheit. This gives the steel memory, meaning the blade will revert to its original shape when bent. After heat treatment, lukewarm water jets rinse off the salt residue and cool the metal to room temperature. Now that the metal has the required properties, the blades need the right profile. A worker lays them on a magnetic plate that angles them downward. The plate spins, running the blades against a grinding wheel. It takes about 30 seconds of grinding to profile each blade and form the flex point, the thinnest and most flexible part that's 1.5 inches from the end of the blade. Blade profiles vary because some jobs require a more flexible tool than others. Now they clean the blades in a revolving drum filled with absorbent sand. This removes oil and other residues left by the production process, and it preps the surface for the protective layer of lacquer that's applied next. After coating the blades in lacquer, they dry them in an oven. This seals the metal, preventing rust. Assembly is completely automated. The first machine slips on the plastic handle. The next machine rivets it on. The following machine slaps on a label which identifies the size and type of putty knife. Professional quality putty knives have a thicker, stiffer blade. The handle is made up of 2 halves. The machine positions them onto the handle portion of the blade, then attaches them with a hollow rivet. This enables the knife to be hung up. This factory also produces retractable utility knives. It puts the cast aluminum handles through a machine that uses polishing stones to remove any shards of metal. Workers assemble the utility knives manually, first installing the push button that moves the blade in and out. After putting in a spare blade, they close up the handle with 1 screw. This factory produces 150 different paint preparation tools for a wide range of uses, from scraping to filling to smoothing out tape on wall joints. The recycling of plastic bottles is changing the fabric of society because those bottles are being turned into polyester yarn. The recycled polyester yarn is woven into material that's used to make socks, fleeces, and other things. It puts a whole new spin on polyester. Polyester is made from oil, so recycling means we get more mileage from a precious resource. They convert polyester manufacturing waste on the left and plastic bottles into chip form. Pulses of hot air toss the chips, giving them hard shells. They go through a dryer to get rid of moisture that would weaken the final product. The shells keep them from sticking together, aiding the drying process. A worm screw moves the chips through heated pipes, which melt them into a thick liquid. This molten recycled polyester is now ready to be turned into yarn. It will be pressed through this die plate that looks a lot like a shower head. It's part of a device called the spin pack, which also includes a mesh filter, a metal distribution plate, and bits of shattered metal for extra filtration. It's important to screen out impurities that might compromise the recycled product. They screw the cap onto the spin pack and insert a metal connector piece. They preheat the pack so the polyester won't harden as it flows through it. Then they transfer it to one of the openings from which the liquid polyester flows. There are dozens of these openings, all capped by a spin pack. "68 tiny holes in each disc shape the recycled polyester into filaments. They cool and harden as they exit. Each one is 5 times finer than a single human hair. Some of it breaks during equipment stops and starts, and that goes into a big box to be recycled again. The rest converges and funnels into a guide, which bundles all the strands into one yarn. The yarn travels around rollers into a compartment where air buffets the yarn to entangle the filaments. This holds them together. A spool then racks up the yarn at a speed of 125 miles per hour. Next, an autonomous vehicle pulls up. The spools move into position, and a long spindle emerges from the automated vehicle to collect them for more processing. They group a sample from every production run with strands of black yarn, which allows the lighter yarn to stand out. They fray both ends of the yarns with a razor, so they'll be easier to examine under a microscope. The technician projects the magnified image onto a screen and counts the number of filaments. At this point, the yarn is stiff like dental floss, but that's about to change. This machinery pulls the polyester yarn over heated rubber rollers. The process stretches it and realigns the molecules. More equipment twists it, and then it's taken up by automated spools. Now, this recycled polyester yarn is less like dental floss and more like wool. From plastic bottles and manufacturing waste to polyester yarn, this transformation has taken just a couple of weeks. This recycled yarn is now ready for the material world, making consumerism a less wasteful thing.
Figurines are made of many materials, from porcelain to plaster to resin. Not the kind that comes from trees, but a synthetic resin, a kind of plastic. It's affordable, lightweight, and easy to use, making it the material of choice for many artists and craftsmen. Each figurine in this collection is cast from a mold of the original sculpture, then hand-painted. This character is a 19th century federal marshal. Working from period photographs of her subject, the artist makes a sketch she'll use as a model. She needs plastic-based clay so it's easier to sculpt. She works on the facial features, constantly referring to the photographs. She usually starts with the figure's head and then adds it to the body. She works from more photographs to create his rifle. It's a delicate piece, so she sculpts it separately before setting it onto the figure. Bearing the artist's signature, it's now ready for casting. First, the sculpture bakes for 30 minutes at 275 degrees to harden. Then, workers cover it with a thin layer of releasing agent so it won't stick to the production mold they're about to make. They place a wall around the piece, tightly seal the base to prevent leaks, then pour in a silicone rubber mix. In 2 days, the rubber hardens enough to hold the shape of the sculpture, but is still flexible enough that workers can remove the original artwork without damage. After removing the retaining wall, suction is used to gently pull the piece from the mold, which retains the sculpture's shape down to every last detail. Now, figurine production can begin. Workers fill the mold with a mixture of resin and flour made from ground pecan shells. This colors the resin and makes it stronger. The mixture sets in less than an hour, and out comes the first of many figurines, an exact replica of the original artwork. The base is sanded to level it. Then, it's stamped with the figurine's name, ID number, and copyright information. Resin is an ideal material for casting because it captures all the details of the original artwork. It creates lightweight, durable reproductions that can be finished in a variety of ways. Here, the first artist coats the figurine's broad areas with acrylic paint. Working color by color, she uses various brushes depending on the areas she's painting. She finishes up with the smaller details. Then, she passes the figurine on to the next artist. This second artist fills in the facial features and other fine details. She starts with the whites of the eyes, then views the figurine from all angles to make sure she hasn't overlooked any tiny detail. Her fine brushwork on the facial features is what truly brings this figurine to life. Bass Reeves' U.S. Marshal is just one figurine in this series that proudly honors the contribution of African Americans in shaping the history of the United States. Once Marshal Reeves passes inspection, workers wrap him up in protective bubble plastic. Each piece in the series comes with a certificate of authenticity bearing the artist's signature, as well as the name and life story of the person the figurine portrays. Collecting this set of resin figurines isn't just for the knick-knack lover. This is indeed affordable art for the history buff. Small-scale figures that pay a large-scale tribute to African-American pioneers.
Retractile cords were invented for telephone handsets in the late 1930s, and ever since, these coiled cords have been making a lot of great connections. From medical equipment to construction tools to industrial machinery, they keep a lot of things plugged in a very neat way. Retractile cords stretch when needed and spring back into a tight coil afterwards. And that means no tangled knots and wiring snarl-ups, which saves time that would otherwise be spent straightening things out. Production begins with thermoplastic colorant. The color selected indicates the electrical function of each wire in the cord. It takes just a small amount to tin a batch of white plastic pellets, a vivid hue, as they melt in an extruder. Tin-plated copper wire feeds into that extruder, and the colored molten plastic coats the wire to provide an insulating wrap. As it exits the extruder, the plastic casing is still warm and soft, but cool water solidifies it. A spool then takes up the insulated wiring. Next, several wires unwind simultaneously over guide rollers and into a spreader plate. The plate precisely aligns the wires as they feed into a die. This die draws them down to the correct diameter, while a mechanism further down the production line twists the wires into one cord. The cord continues to twist as rollers wrap polyester-backed foil around it. This foil is a shield to protect the wires from electrical interference and is an optional feature. The cord then passes through the twisting mechanism and onto a take-up reel. Next, standard unshielded cord travels through beads of electrodes as thousands of volts of electricity are applied to them. The energized electrodes detect any faults in the wires. If they find none, the cord moves forward. The next machine gives the cord a paper wrap. That's followed by the final layer, a thermoplastic jacket. It also takes a trip through a cooling station to solidify. An inkjet printer applies technical and other information. The plastic casings of some cords have been treated with fire-retardant chemicals. Now they put that treatment to the test. The cord doesn't catch fire, confirming that it's flame resistant. So it's now ready to be coiled. This worker gets the process started by manually winding it around a rod. Then he presses a button and the automated winder does the rest. This establishes the spiraling profile of the retractile cord. But at this point, the coil won't hold. Simply pulling out the rod would cause it to unravel. The plastic sheathing around the wires has no memory, so it won't retain the shape. They wheel the cords, still on rods, into an industrial oven and bake them at 200 degrees Fahrenheit. This gives the cord's plastic casing the necessary memory, so that when the operator pulls out the rod, the coil is intact. But it still doesn't have the necessary snap. That is now achieved by reversing the direction of the coil. The equipment used for that is proprietary, so this worker demonstrates the basic concept with the drill. The drill turns the cord counterclockwise for an impressive rewind. The effect ripples all the way down to the end. Reversing the direction of the coil transforms it. The process tightens the spiral so that after the cord is stretched, it retracts to its original shape. The difference is very apparent. The top coil in this shot hasn't been reversed, while the bottom one has, and it's clearly much tighter. So these retractile cords are now ready to be stretched to the max and snap right back again. You might not have noticed, but road signs have undergone a subtle change in recent years, thanks to advances in technology. Today's signs are more reflective than ever. You can actually read them in the dead of night, even when the only source of illumination is your car's headlights. The earliest road signs were crude: a stick in the ground or a heap of stones to mark a route. In the Roman Empire, stone posts were erected along roadsides at regular intervals, indicating the distance to Rome. Centuries later, stone marker systems gave way to wooden cross signs pointing in several directions at once. The international system of road signs we know today came out of the first International Road Congress held in 1908. The process of manufacturing a road sign starts with the computer. The government strictly regulates the specifics of the design and requires a certain degree of reflectivity. The computer's specialized software guides a machine to cut the design on a sheet of film. Once the design is cut, workers carefully peel off and discard the pieces. What's left is a film stencil of the sign, in this case, a French stop sign. They inspect it for defects, then prepare a screen of polyester fabric that they'll later use to print the sign. They start by coating it with a thin layer of light-sensitive emulsion. Once the emulsion's dry, they adhere the film stencil, using vacuum pressure to flatten it and get rid of any creases or air bubbles. Then they expose the screen to an intense 6,000-watt light for 7 minutes. This activates the emulsion on the lettering and area outside the octagon, what's not shielded from the light by the film stencil. This exposed emulsion hardens, plugging the minute holes between the screen's fibers. After rinsing, you see the result. Elsewhere in the factory, workers cut the aluminum panels on which the signs will be printed. Using a punch press, they round out the edges and make holes for the bolts that'll later attach the sign to the post. They stamp on the company name and the year of manufacture for warranty purposes. They immerse the panels in a chemical bath to remove grease and other residues. Then they rinse off the panels and dip them in an acid solution that seals the metal to make it better withstand harsh weather. Next, they laminate the aluminum panels with a film containing minuscule glass particles. This film will make the sign reflect in the dark when light hits it. Then they cut the panel to the final shape. Now they can finally print the sign. The process they use is called silk screening. Although the fabric screen, as you saw earlier, isn't actually silk, it's polyester. The machine forces the ink down through the screen onto the panel. The ink penetrates through the open fiber holes of the octagon, printing the red background of the stop sign. But it can't penetrate through the blocked fiber holes of the lettering and the area outside the octagon, so those remain white. The freshly printed signs pass through a dryer at about 150 degrees Fahrenheit for 5 minutes. To produce street signs, workers first laminate aluminum panels with reflective film for the background color. Then either silk screen the street name or apply self-adhesive reflective lettering. But it's back to the silk screening process for printing multicolored signs. Workers print them one color at a time, with a drying cycle between colors. All the film stencils are carefully stored for future use. The printed signs go into an oven for a final curing at 349 degrees Fahrenheit. An hour for a one-color sign, a half hour per color for a multicolored sign. The ink is transparent enough not to block the reflective film underneath. Therefore, the entire sign, not just the lettering, is highly reflective. That maximizes the sign's visibility, thereby minimizing the excuses drivers can come up with for not heeding it. For centuries, inventors tackled this challenge with determination and frustration. The first snow machines trudged through winters awkwardly and slowly. But by the late 1950s, new technologies and materials emerged to make snowmobiles that could blaze through the snow with increasing ease and comfort. Snowmobilers often face rugged terrain. Snowmobiles need a rock-solid build to keep the rider safe and comfortable. It all begins with an aluminum alloy frame. The pieces arrive partly assembled to the radiator. The robot spins and positions the frame. A computer-guided frame rivet machine punches holes and inserts rivets directly into the frame with great precision. This process bonds the parts tightly so they can't vibrate. Next comes the rear suspension, aimed at making the ride as smooth as possible. Inserting this plastic slide onto the runner minimizes friction between the track and the suspension. A conveyor belt carries the suspension system through several stations. Wheels and sprockets will turn the track that grips the snow. The suspension kit with springs and coils goes directly into the runners. Along with these shock absorbers, the suspension will fit snugly into the snowmobile's frame. Workers tighten everything manually for now. Later, a machine will tighten things even more. Assembling the transmission system starts with this countershaft. First, they install a high-performance brake disc made of forged steel. The chain case fits snugly on top thanks to the ridges on this ring. This die-cast aluminum casing will house 2 gears and a chain. This bolt connects to a spring that keeps the gears and chain tight as they turn. The chain tightener must slide smoothly back and forth in its groove to keep the chain's tension even. This test checks that the spring expands and compresses properly. Now comes the oil gauge. It's essential that oil lubricate the parts thoroughly because the motor will generate a lot of friction. The transmission fits on top of the frame. These coils, springs, runners, and wheels fit easily into the rubber track. The rear suspension system connects to the track system while this white plastic sprocket connects the track to the transmission. The speed sensor attaches directly to the sprocket. Four high-grade steel bolts anchor the rear suspension system to the frame. They're so strong that the suspension can withstand the vibrations that come with high speeds. Now for the engine assembly. Bolts attach the electric starter directly to the engine. The fuel-injected engine generates a lot of heat, up to 1,300 degrees Fahrenheit. This shield has layers of insulating wool that act as a heat barrier to protect the driver from scorching hot exhaust. The engine's made of cast aluminum, so it's relatively light, just 100 pounds. And it propels the snowmobile up to 120 miles an hour. Now for the front of the snowmobile. This front suspension system requires a different assembly from the rear one. A hoist brings it all together. The gas tank is made of lightweight molded plastic rather than metal. The throttle controls the speed just like a gas pedal in a car. They install the throttle assembly and a few more functional details. These lightweight aerodynamic plastic side panels give this snowmobile a sleek look. And now the final step. The zero-gravity hoist lifts it all onto a skid. Polystyrene sheets protect the snowmobile during transport to the retailer. From start to finish, it's taken 3 hours to assemble this showroom-ready snow traveling machine. Soy sauce is a staple of Asian cuisine, used as both a condiment and cooking ingredient. Its roots are in the seasonings of ancient China. Today, you can buy artificial or chemically enhanced versions, but authentic soy sauce is all natural and made the traditional way, by brewing soybeans and wheat. At this small soy sauce company, they use the centuries-old slow fermentation method and just 5 ingredients: soybeans, water, wheat, sea salt, and yeast. They begin by pouring soybeans into a cooking device called a steam kettle. After thoroughly rinsing the soybeans twice, they fill the kettle with water. Then close the lid and boil the beans for 4 hours. Meanwhile, they pan roast wheat in a skillet for about 25 minutes. Then they put the roasted wheat through a mill. The mill's steel rollers crack each grain into several pieces. This will enable the yeast to better penetrate the wheat during the fermentation process. When the soybeans are ready, they take them out of the kettle and spread them out in large trays to cool. When the beans cool to 91 degrees Fahrenheit, it's time to add the wheat. After mixing everything thoroughly, they sprinkle on yeast and mix again. The ingredient proportions are key and therefore a company secret. To activate the yeast, they transfer the mix to shallow boxes and stack them for about 48 hours in a controlled incubation room. This process generates heat which rises, so they have to gradually move boxes to lower racks to prevent overheating, which would kill the yeast. For the next stage, they make a brine by mixing fine sea salt with spring water. To give its soy sauce a distinctive taste, this company repurposes bourbon barrels from local distilleries to use as fermentation vessels. Traces of bourbon in the wood permeate the mix as it ferments, imbuing the sauce with a subtle smoky and sweet flavor. After dissolving the sea salt in the spring water, they add the soybean mix, creating a murami, the Japanese word for soybean mash. They blend for a few minutes, then seal the barrel and leave it to ferment. For the first 6 weeks, once daily, they open the barrel and mix the murami to aerate the gases that build up. This keeps the yeast active and helps develop the flavor. Then, after that, they open and mix just once a week. After 12 long months of fermentation, it's finally ready. They open the barrel and mix one last time. Then they empty the barrel onto a sheet of muslin lining the tub of a stainless steel press. They fold over the sheet to enclose the murami. Then lay down planks of wood to form a solid surface. The press applies 6 tons of pressure, forcing the planks downward against the murami. This squeezes out all the liquid, which is the soy sauce. It exits through a hose at the base of the tub and moves on to be filtered and heat pasteurized. The pressed murami gets a new life as high-protein animal feed. While many soy sauces are mass-produced, this factory brews small batches at a time. A batch yields about 600 bottles, each of which workers here fill manually. They top each bottle with a plastic diffuser, which dispenses just a dash of sauce at a time. Then they twist on a plastic cap and slip a shrinkable plastic band over it. Using a heat gun, They seal the band tightly around the cap and bottle. Then the label, on which they write the batch code and bottle number by hand. A fitting finale for this signature soy sauce.